Assalamu alaikum everyone, I hope you are doing well and taking good care of yourselves. This is your instructor Ali Faruqi and you're watching Science with Ali. So in today's video, we're going to be starting a brand new topic called reversible reactions and equilibrium. And the objectives for today's lessons are: what are reversible reactions, what do you mean by the term equilibrium, and what does position of the equilibrium mean. So let's just start right away. Now, when we look at chemical reactions, we see something like this. Carbon plus oxygen will give me carbon dioxide. So what happens here is that carbon and oxygen react together to form carbon dioxide. Means that this is a one-way reaction. The reactants get transformed into the products. This means that once the carbon dioxide is formed, it will not turn back to carbon and oxygen independently, individually. So when we talk about a chemical reaction that is reversible, we have something like this. Ammonium chloride gives us ammonia and hydrochloric acid. Now this double arrow in between tells us that this whole reaction is reversible. It can either go forward and it can also happen backwards, which means that this ammonium chloride can decompose to form NH3 plus Cl in the forward reaction, and the same NH3HCl will go back to form NH4Cl, that was a reactant in the forward reaction. So we call this the backward reaction, right? This basically looks something like this. The first equation that I showed you was for the one-way reaction in which the reactants can turn into the products only, and that's it, the reaction ends. But in this case over here, it is a round trip, as it is written over here. The reactants get turned into the products, and then the products get turned back into the reactants, right? So the definition for reversible reaction is as follows: a reaction where products can reform original reactants. The forward reaction is left to right and the backward reaction is from right to left. Now, the one thing to understand is that these reactions can take place at different rates, which means that at the start of the reaction, the ammonium chloride will be present only, and the forward reaction will take place first to form the products, and after the products have been formed, will the products then react with themselves to form the reactants again, which means that at the start, the forward reaction rate is fast because more ammonium chloride is present. The only thing which is present in the reaction mixture is the ammonium chloride. So the first reaction which is going to take place will be the forward reaction, and the backward reaction won't have started just yet because it is still forming. The products are still forming, which will enable the backward reaction to happen. However, as the reactants turn into the products, the forward reaction will slow down and the backward reaction will speed up, which will indicate to us that after a while the rates will even out and the backward reaction will be going at exactly the same speed as the forward reaction, which tells us that the reaction is in equilibrium, right? Now, what do you mean by the term equilibrium? Equilibrium states that is the state where the forward and backward reaction are going at exactly the same speed as we discussed over here. Another concept which arises is that the concentrations of the reactants and the products won't change anymore. The concentrations of the reactants and the products are constant at equilibrium, but they are not the same. For example, there could be lots of NH4Cl present as a reactant and small amounts of NH3 and HCl present at equilibrium, but the concentrations of the reactants and the products will remain same. As for the same case, that for example, if there's a lot of NH3 and a lot of HCl present at the product side and a small amount of NHCl present on the reactant side, at equilibrium the concentrations will remain same. In either case, as long as the forward and backward reaction rates are the same, going at exactly the same speed, the reaction would still be at equilibrium. What would change when we have these different concentrations is the position of equilibrium. Now, what is meant by the position of equilibrium? What this basically means is that whenever we have more product than the reactants, we say that the equilibrium position lies on the right. But whenever we have more reactants than fewer products, equilibrium position lies to the left. Let's explain this more clearly. This position of equilibrium can change depending on conditions. For example, adding heat to this reaction encourages the forward reaction, as adding heat to this reaction will encourage the equilibrium position to go towards the right, which will end up in you having more products, right? On the other hand, if we cool the conditions of the reaction, like we just did above, which was heating, we first heated it. Now the equilibrium position has moved to the right. We added heat. But now if we cool it, if we put it in a freezer, for example, it would push the equilibrium position back to the left. So we would have more NH4Cl again. Regardless of the position though, equilibrium can only be reached if the reaction is done in a closed system, like for example some sort of sealed container or some sort of sealed room in which the reactants are kept and the products are kept, so that the products cannot escape the reactant and the reaction can stay in equilibrium, like represented over here, in which the chemical reaction is in equilibrium because it is done in a closed system. The reactants and products are not able to escape this system, meaning that the reactants get transformed into the products and the products then back up get used into the reactants, meaning the reaction is in equilibrium. On the other hand, if we look on the open system that is represented over here, we can see that the products are leaving the container. Keep these people, you can just ignore these people, right? They are the products in this reaction. So they are the products, and therefore the reaction is not at equilibrium. Why? Because the products are escaping, and this will result in all the reactants getting used up, and it will just turn into a normal chemical reaction and not a reversible reaction. Right, now that this is clear, the last thing that we need to cover is that reversible reactions are always exothermic in one direction and endothermic in the other direction, like so. As you can see over here, that in the forward reaction, this chemical reaction is endothermic because decomposition is happening. I have explained decomposition in the chemical energetics video. If you haven't watched it yet, I will link it below the like button, so you can just go and watch it. I have uploaded the full playlist of it as well. So a decomposition reaction is when a compound is breaking into two or more simpler compounds or elements, right? So as you can see over here, this whole NH4Cl is breaking down into NH3 and HCl, so it is an endothermic process in the forward reaction, and because it is endothermic in the forward reaction, it will automatically be exothermic in the backward reaction. For example, if we look at this reaction shows the thermal decomposition of hydrated copper sulfate into anhydrous copper sulfate plus water. If you're unfamiliar with these hydrated and anhydrous terms, hydrated just means that water is present, and anhydrous means that no water is present, right? So if I explain this to you with the help of a diagram, we can see that thermal decomposition of hydrated copper sulfate means we add heat to this, which will give us anhydrous copper sulfate and water. Initially, before the reaction starts, our reactants, the hydrated copper sulfate, are blue crystals. But if we start decomposing them, if we start heating them, it would drive the reaction to the right, meaning that the reaction will start to break down the hydrated copper sulfate, and anhydrous copper sulfate and water will be formed quickly and quickly. Because the reactant's concentration is decreasing, the product's concentration is increasing, meaning that equilibrium shifts to the right. Now, after the reaction is done, after the forward reaction has been completed, the backward reaction will start. So if we add some water to favor the backward reaction, the white anhydrous copper sulfate powder that was left, it would drive the backward reaction if we added water. So the equilibrium position will shift to the left as reactants are now increasing again and the products are now decreasing, right? So this would reform our blue crystals of the hydrated copper sulfate that we heated to form the anhydrous copper sulfate in water. And because the backward reaction is exothermic, because the forward reaction was endothermic as it was decomposition, it would re-release all that energy which was absorbed in the forward endothermic reaction. Let's make a point over here. Right, so after adding water, the backward reaction will be favored, as we know, and because backward reaction is exothermic, it would re-release all that energy which was absorbed in the forward endothermic reaction. Because the endothermic reaction takes in energy from the surroundings, it would re-release all that energy, meaning the temperature of the surrounding will increase back again because the backward reaction is an exothermic reaction. So this wraps up part 1 of our reversible reactions video, in which we discussed what are reversible reactions, the term equilibrium, and the position of equilibrium. In the next class, we will be looking at Le Chatelier's principle, in which we discussed how temperature, pressure, concentration, etc., the conditions which are tampered with, what effect do they have on the position of equilibrium. So stay tuned for that. As always, if you have any questions regarding this video, so please drop it down in the comment section down below, so I will respond to your questions. Anyway, so I hope you enjoyed this video, and I will see you in the next class.